Okay, worksheet 6.2. So in this section, instead of doing a hypothesis test where we have some value that's given to us that is assumed to be true, and then we take a sample and compare our sample to this known value, we're going to take two different samples and compare them to each other. And sometimes we're hoping that the samples are the same, and sometimes we're hoping that they're different, and sometimes we're hoping that one sample is larger than the other. It just depends on the situation. So, suppose you own an ice cream truck that is doing very well in a Farron. Oh, that's nice. First sentence, already made a mistake. And you are considering purchasing a second truck and keeping it in Huntington, but you are unsure if those rascals on that side of the county like ice cream. To aid your decision, you take a survey of 250 random people in Farron, and you find that 210 of them like ice cream. So let's put that in here. So 250, so 210, which means how many did not like ice cream? 40. In Huntington, you survey 300 people, and you find that 219 of them like ice cream. So 219, 300, so this must be 81. Okay. So the totals going across would be 429 and 121. So that's going to be 550. Now, we can actually look at this vertically or horizontally. So we could look at this as cities, which is what we're going to do. We can also look at it as people who like ice cream or don't like ice cream, and we can calculate the numbers going across. So it doesn't really matter what order you put them in. You're either going to work vertically or you're going to work horizontally. All right, number one, which is the explanatory variable? Are we wondering if ice cream people live in a certain city, or are we worrying about a city having particular ice cream preferences? We're looking at the city having ice cream preferences. So the explanatory variable would be cities, and the response variable would be ice cream. Now, does that mean that living in a city causes you to like ice cream or not like ice cream? No. But that's just the way we're comparing it. We're comparing cities together according to their ice cream preferences. Okay? So what percentage of people in Farron like ice cream? So let's pull up my calculator's not even on. All right, so 210. Oh boy. So 210 out of 250. So 0.84. And then in Huntington, we get 219 divided by 300. And we get 73%. So do you think that those proportions are far enough apart to suggest that the two cities have different percentages of people who like ice cream? And that's totally a judgment call. Essentially, we're asking, do you think we're going to accept the null hypothesis, or do you think we're going to reject the null hypothesis? So give your best guess. Okay. Next, what would the null hypothesis be? Well, we're dealing with proportions, so what variable are we going to use? You're welcome. Whoa, don't steal my stylus. So, what is our variable for population percentage? I'll give you a hint. It's either pi or mu. Pi. So, our H naught is our H naught is saying that our two cities have the same proportion. Remember how our null hypothesis is always equal to? Now, there are lots of ways you can write this. Don't write this down. You could say that the population percentage in Farron is equivalent to the population percentage in Huntington. That would be one way to do it. And it doesn't really matter how you do it, but our Zybook does it a different way. And it says, instead of saying they're equal, it says that the difference between them is 0. Right? And that kind of makes sense because we are calculating the difference here. So it makes sense that the null hypothesis is written in terms of the difference. Now, does it really matter which one you put first? No, not really. Sometimes we want to know if one city is greater than another city. So we would probably put the bigger one first. But it doesn't really matter because when we get to the alternative hypothesis, we could just switch the greater than to the less than, and it doesn't really make a difference. Okay? So for the alternative hypothesis, is there any reason why we think, do we want one of these to be greater than the other, or are we hoping that they're equal to? So basically, is this a one-tailed test or a two-tailed test? And we'll write that here in a second. So for the alternative, is there anything in the original question that is asking, is Huntington greater than Farron, or is Huntington less than Farron? Or is it asking, are they different? So if Huntington is the same as Farron, are you going to buy the truck and use it? Yes. So all we want to know is if they're equal. So we would say that the proportion in Farron minus the proportion in Huntington is not equal to 0. Oh, wait a minute. Well, I guess, maybe I want to change my mind. I want to know this. Because if Farron is greater than Huntington, are you going to buy a truck? No. If they're the same, are you going to buy a truck? Yes. If Huntington is bigger than Farron, are you going to buy a truck? Yes. So we do want this to be one-tailed. Well, yeah. So for our purposes, equal to is good enough, but the null never has an equal to because this one does. If there was an equal to, then you would actually accept both. So for our purposes, H equaling F is a win, and H bigger than F is a win. The only time we don't win is if H is smaller than F. So yeah, for our purposes, an equal to is great. But for the null hypothesis, it's never greater than or equal to. It's always greater than or less than or not equal. Oh man, that is so small. Let's do this. Okay. So, number 7, what is the actual difference between the two sample proportions? How far off were they from each other? So it would be 84% minus 73% is it 7%? It's 7 percentage points. Now, if you write 7%, that's fine. But that's not a percentage, that is percentage points. Remember, if you use subtraction, you're talking percentage points. If you use division, you're talking about percentage. Okay. So think back several chapters. Number 8. What is the formula for the standard deviation of the probability histogram for each sample? So remind me what a probability histogram is. Nobody remembers? Okay. That's why I put this question on there. So I took a sample in Farron and I got 84%. Right? If you took a sample in Farron, are you going to get 84%? No. But you'll probably get something close to it. Right? So maybe you get 82%. What is the true proportion in Farron? We don't know. That's the whole reason we did a sample. So if lots and lots of us take samples, eventually we're going to get something that looks like a normal curve. That curve is called the sampling distribution. And that is a normal curve that is created by sampling Farron many, 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 many times. And regardless of the makeup of people in Farron, the sampling distribution is always going to be normal because the true value is out there. So let's say the true value is 80%. So every time we sample, we should get a number close to 80%, but it's not going to be perfect every time. And so if we graph everybody's sample values, we get a sampling distribution. Okay? And then if we look at the sampling distribution and we measure this distance right here, that is the standard deviation. Or if we take everybody's sample and graph it and compute the standard deviation, I get the standard deviation of the sampling distribution. Is this coming back? Okay. What is the formula for calculating the sampling distribution standard deviation? So it was the square root of p hat times, well, I guess it's pi. So pi times 1 minus pi over n. So it's basically the probability of success times the probability of failure divided by the number of people in the sample, and then you take the standard, square root. Hello? Yes. Okay, you're right. You're being picky. It's not 7 percentage points. It is 11 percentage points. Because I can add. All right. So what is the standard deviation for the sampling distributions for each sample? So we're going to take the square root of, well, maybe, so I can push the right buttons. So the square root of 0.84 times, if the probability of success is 0.84, what's the probability of failure? 0.16, and then how many people are in that sample? 250. And then we get the square root of 0.73 times 0.27 divided by 300. Does that make sense? So what we've done is we have created two sampling distributions. One represents Farron, one represents Huntington. And the standard deviations for each of those, so this one is 2.56%, and this, nope, I got that backwards. So this is 2.31%, and this is 2.56, and again, it's percentage points. Okay? So, I want to compare my Farron sample to my Huntington sample. All right? I want to create a sampling distribution, essentially, where I take all of the Farron numbers and I subtract all of the Huntington numbers, and I get a new sampling distribution. And that new sampling distribution will have a standard deviation that is based off of the original two standard deviations. And the formula that they put in Zybooks was correct, but it was really confusing because I don't know. I'll show you what it means. So, in my end resulting curve, what do I assume that the difference between the two cities is? 0. My null hypothesis says we're going to assume that Huntington and Farron are exactly the same. If that's the case, then my Huntington value minus my Farron value should be 0. So my normal curve will have a center at 0, and the standard deviation for this curve is going to be the square root of Huntington squared plus Farron squared. For SDs, sorry. That's going to be confusing. So we take the SD of Farron squared plus the SD of Huntington squared. And that formula looks really familiar. It's the Pythagorean theorem, right? So it's like saying C squared is equal to A squared plus B squared, and then you just take the square root. That formula shows up in so many places that has nothing to do with right triangles. But essentially what's going on is, if you take your Huntington SD, oh, I did it again. So if you take your SD from Huntington, or Farron, and your SD from Huntington, the SD for the difference is going to be the hypotenuse of that triangle. And that's a relationship that shows up all over mathematics, even though it has nothing to do with the triangle. So in Zybook, this is what they said the formula was. Do you get that? So this is your SD for Farron, and this is your SD for Huntington, and then the SD for the difference. Oh wait, there should be a square root in there, huh? Each of these should have a square root. So that's the formula they threw at you, and it's correct, but I think it makes more sense to say your SD for the sample is the square root of pi times 1 minus pi over n, and then your SD for difference is simply the square root of SD1 squared plus SD2 squared. And those mean exactly the same thing, but it's a little bit messy when you throw it all together in that original equation. Okay? All right. Go back here. Oh, I lost it all. Forgot about that. Okay, so I ended up with SD for Farron was 2.331. My SD for Huntington was 2.56. And my normal curve assumes 0. And what was our value? What was our actual difference? 11. So this is 11. And I need to take the square root of 2.31 squared and add it to 2.56 squared. All right, so square root 2.31 squared plus 2.56 squared, and I get 3.44. So this distance right here is 3.44. That's my SD. So, sorry, I went a little fast, but that was 10 and 11. Did everybody get the formula for 10? So 10 is the square root of SDF squared plus SDH squared. And then the answer is 3.44. All right, number 12, is this a one-tailed test or a two-tailed test? One-tailed, because I really only care about one side. If it's equal to, or if Huntington is equal to or greater than, we're going to buy a new truck. But if Huntington is less than, then we're not going to. Okay? So what z-score creates a p-value less than 5% in a one-tailed test? So do you remember when we were drawing p-values? So if p is less than 5%, what number is that in a one-tailed test? How many standard deviations was it before we rejected the null? And I didn't expect you to remember this. It's about 1.65. So if your z is bigger than 1.65, we reject the null in a one-tailed test. If your z is smaller than 1.65, we accept the null. What if it's a two-tailed test? So if this is 2.5 and this is 2.5, what value is that? And it was about 1.96, about 2. Right? Because at 95 at 2 standard deviations, we capture 95% of everybody. Right? Which leaves 2.5 on either side. So those are the numbers we're going to use today. If you have a one-tailed test and p is bigger than 1.65, we reject the null. If you have a two-tailed test and your z is bigger than 1.96 or negative 1.96, then we reject the null because the p is less than 5. Okay. All right. What is the z-score for the difference between the two samples? So here's my picture. How do I do z-score? Well, I need to figure out how far is my value from the average, or from the expected. So how far is this? 11 minus 0. And then I need to convert that into standard deviations. So I'm going to divide it by 3.44. So I get 11 divided by 3.44. And I get 3.19. So my z is 3.19, which means my p-value is greater than 5, less than 5? Less than 5, right? The farther away I go, the smaller the area on the corner becomes. Already sick of me? I don't have any idea. All right, so the farther out I go, the smaller the p-value becomes. So am I going to accept the null or reject the null? Reject the null. Okay. So number 16, is there evidence to suggest that the cities have the same proportion of people who like ice cream? No. Nope. So we reject the null. Are you going to be buying a truck? No. Because Huntington had less than Farron. All right? So 17, is there evidence to suggest that living in a particular city causes people to like or dislike ice cream? No. Why not? It's not what we were testing, that's true. But was this an observation or an experiment? Observation. Did the people choose what city they lived in? Well, I mean, you did, right? You don't have to live in a city. You could walk away at any point, right? If you're living in a city, there was some choice. So in order to say that A causes B, we have to be able to randomize oh my goodness, I'm too tired. What's the phrase they used? Randomize the treatment and control. You remember that? So we had randomized this random sampling and we had random assignment. That's the word I'm looking for. Were these people randomly assigned to their two cities? No. So can we say that A causes B? No, because there's no random assignment. So in order for in order to have evidence that says that A causes B, we have to do random assignment, and some people get the treatment and some people get the control. And in this case, that didn't happen. So we cannot say that living in a city causes A or B. All right. Do you want to try one on your own? Okay. I'll work on the answer sheet. So I'm going to pause the video and let you guys work through this, and then I'll answer questions. And then you can do the one on the back all by yourself. Okay? So if you're at home, finish the second page and then unpause the video. Okay, let's finish this up. So in this case, we are assuming that homework is the explanatory variable and that competency on the test is the response variable. Those are the two percentages. And then our null hypothesis is the percentage for the homework doers minus the non-homework doers is 0. And the original problem asked, is there a difference between the two? It didn't say one was greater than the other. So that would be a not equal to null hypothesis. Our actual difference, if I subtract my answer for 19 and my answer for 30, the students differed by 1.1 percentage point. So I use those to create the standard deviations. So I do the square root of 0.407 times 1 minus 0.407 over, let's see, I divide that by 145. Oh, did I get that right? Oh, I did that wrong. Sorry. I divided it by the wrong number. 0.337. Does that sound better? And then the next one. So the did homework. Well, let's write this out. So we're going to take the square root of 0.407 times 0.593 divided by the total number of homework doers is 145. Okay. Oh, there it is. So 408. And then, anyway, so for this one, you should accept the null hypothesis. And then tomorrow, we are going to do the next problem. So, good luck.